Okay. Just a brief video here about this, I guess I want to call it just like an additive synthesizer, basically. And this started because I wanted to experiment with adding some amount of inharmonicity. And inharmonicity is this phenomenon where the overtones of usually a real-world system, a mechanical system, are not exact integer multiples of the fundamental. So this is a big problem with tuning pianos and with other kind of similar, like bars or strings that are struck often have inharmonicity. So the kind of general wave shapes we use when we're using synthesizers have perfect overtones. And that is, the overtones match the integer multiples of the fundamental. And so in order to get the overtones to not match, I can't build the wave shapes directly by, using an equation for a line to make a triangle wave or a sawtooth wave, and I can't just, pump out ones and negative ones to make a square wave. Those will all give me those kind of perfect harmonics as overtones. So instead I've built this network of individual oscillators that I can control the pitch of discretely. And I have this inharmonicity factor here, which you can see changes the values of these individual oscillators. So if I drag the fundamental here to something that's really obvious, easy to see, say maybe if I set it to 220 by hand, which is an A, then bang, 220, 440, 880, 1320, those are the even order harmonics, odd order harmonics, 660, 1100, etc. But as I drag the inharmonicity, then the fundamental is still at 220. This is the first factor of 1 here times 220. That's great. But now all the overtones are no longer integer multiples, and they get worse the higher that you go, which seemed to be the correct thing to do. I watched a couple videos and did some research about the way that the inharmonicity kind of stacks up in real life, and at higher and higher orders, the factor off from the intended integer multiple increases. So I've used this equation here, which is f naught times n to the power of x. So n is the harmonic and x is the inharmonicity factor. So I'm increasing this inharmonicity factor, which is in this power here, and so the larger n is, the larger the factor is away from what it's supposed to be. So for example, if n equals 2, then well, we can just do it. Let's just do some actual examples. So we know that this one's supposed to be 440, and it's 15 away. And we know that this one is supposed to be 880, and it's a lot more than that away. It's almost 60 away. So right there, you can see it's supposed to be 440, it's supposed to be 880. And that's what we kind of expect, because our perception of hearing is log-based. But even still, I guess if these scaled, so I just touched the slider again, so now this is 5 away. This is double, so maybe it's about 10 away. So that's more or less what we expect, to have that kind of same scaling. So each is kind of a constant difference in terms of perception. So yeah, the other thing I can do with this is kind of add the harmonics themselves. So this will have kind of a similar effect as to opening a filter. You're kind of increasing the harmonics themselves. So basically there's just a, this is just like a volume knob on, it's the same on all of the individual, or no, sorry, this is also scaled, so that the harmonics are still kind of falling off at some rate, and that's because that's what happens when we want to build these individual wave shapes as a sum of sines. You know, if you look at a square wave, the third harmonic is a lot stronger than the fifth harmonic, is a lot stronger than the ninth harmonic. I guess I skipped 7, but they fall off as actually at a rate of 1 over n. So the coefficient to the third harmonic is 1 over 3, the coefficient to the fifth harmonic is 1 over 5. So we can dial that in actually by leaving this at -1. Triangle wave, the harmonics fall off even faster. It's a coefficient of 1 over n squared. So that's why this, it's only odd harmonics, so that's why this is all, the even harmonics in both these cases are over here at -5, which doesn't set them all the way to 0, but they're essentially trivial at that point. So now the coefficients of the odd harmonics are changing at this rate of 1 over n squared for the triangle wave. And for the square wave, the coefficients are there's both even and odd order coefficients, and they're both falling off at a rate of 1 over n. So that's why the even harmonics jumps up to -1 here. So this is basically the coefficient. So n to the power of -1 is the same as 1 over n. So each coefficient you can see, this is 1/3, that's the coefficient right there. This is 1/5, this is 1 over 7, this is 1 over 4. So it's kind of, this is 1 over 8. It's easy to see. That way, these are the individual coefficients. Each individual oscillator, which is ultimately mimicking one of the harmonics and adding an overtone, gets its own scale factor. So this is a cool way. It is obviously different than a filter, most specifically because I can independently control the even and odd order harmonics, and I can create some kind of unnatural wave shapes. It'd be very unusual for a wave to have harmonics that are louder than the fundamental. We could do that, of course, with a high-pass filter or something, but as we drag this up past -1, and especially into positive values, you start to get really weird wave shapes that you wouldn't ordinarily see. And yeah, we can play around with all this. I'm just going to trigger a little sequencer here, basically, and we'll see what this all sounds like. Okay, so this is just a basic sine wave, setting both of these as low down as possible. So I wanted to give them a reasonable range of motion, which is why I capped it at -5, but you can see this looks pretty sinusoidal. Go to square wave. So let me just so you can kind of see that these look the way that they're supposed to. Oh, the reason they don't is because the inharmonicity is not 1. So if I do that, and then snap it back to the prestate, there we go. But now as soon as I start playing with these things, that's all going to change. So you can hear how really sharp and buzzy that is when we drag those harmonics up. It's a pretty nice sounding one right here, actually. And you get a nice out of tuneness, and if you can lock onto a single pitch, if you can listen to the fundamental as I drag up the inharmonicity, the fundamental doesn't change, it's only the overtones that are changing, which is kind of a unique phenomenon. something a little more consonant. Still a little too much. That's kind of nice. When I drag this all the way down, it has a very bell kind of quality. You can imagine a bell as like a kind of a weird mechanical structure that you can strike, and the overtones are not necessarily perfect integer multiples of the fundamental. So just to my ear, pulling this really low, and this means now instead of in the below one, that means the overtones are now less than the integer multiples they're supposed to be. When it's above one, it means that they're more than the integer multiples they're supposed to be. So this is a very bell-like quality to me. Might be the way that an early synthesizer, before we had like sampling keyboards that just essentially had high quality samples of actual instruments, we kind of tried to mimic those sounds by using different wave shapes. That's probably a way some of these early kind of modeling synthesizers, those cheesy sounds we think of are attempts to sound like a real acoustic instrument, but just fall really, really short. Because, we only have so many orders that we can work with here. So I think I'm going up to 21. All right, so these are all the even harmonics, these are all the odd harmonics. So I'm going from 1 to 21. Yeah, and that's really it. The very unique and distinct sounds of the individual odd order and even order harmonics. It's nice to be able to hear those individually. If I was really adventurous, I could put an individual inharmonicity factor for the odd order and the even order, and then it could kind of mix them, put the even order above and the odd order below or something, and get really, really complex sounds that way. So maybe that'll be the next iteration.